In this video, we'll be looking at functions such that it is x equals instead of y equals. Now this appears like it's going to make drastic changes to the overall concept of how to evaluate these integrals. However, everything that you think of, you just think of in the what we call inverse way. So, for this particular function or set of functions, what we're going to do is we're first going to start by viewing this as x equals 4 minus y squared as something like y equals 4 minus x squared. If I think about it in this way, I know how to graph this function. Again, it's shifted up 4 units and it's a quadratic facing down. So this function would normally look something like this. Okay? Knowing that the function looks normally something like this, what I can do is I can argue, well, it's going to be an x equals instead, and it's going to be y squared instead. Which means that if I were to take this and I were to change this to a term of x and y, this is really the function I'd be looking at for this case here, as opposed to this here. Now keep in mind, this is not the function we're actually working with. It just gives me a guide in terms of knowing how this graph is supposed to look. Now keep in mind, if I were to try and flip this so that it's the normal coordinate axes that I work with, I'd put the x over here and the y over here, and you'll notice this is in the positive side of x, if I had x up here, so this is going to be over here. And this is the, again, working towards a negative side of x, such that it passes through the y-axis. So that first function would look something like that. Now keep in mind, this isn't a function. This is just an equation, but we still want to find the area between these two graphs. So there's my first graph setup. The second one, again, we're going to treat very similarly. Now, again, first idea is I want to look at it as though it's y equals x squared minus 4, which I know is nothing more than a quadratic shifted down 4 units and facing up, so it's going to look something like this. But again, if I visualize this as though this is the x-axis and this is the y-axis, then I'm no longer looking at that function, I'm looking at this one here. By looking at this one here, I'm going to go ahead and flip that function so that it appears appropriately. Now remember, x has a negative value to start, so that's over here. This is my x-axis, this is my y-axis, and it has a negative axis and it moves towards the y-axis, so it's going to graph this direction. So now, if I were to take these two graphs and put them together, because again, I want to find the area between this curve and this curve, I would see more appropriately 1, 2, 3, 4, 1, 2, 3, 4, the graphs that look like this. And again, the idea is I should be able to, and I messed that one up, I should be able to see the intersection point between these two graphs. There's an intersection point here and an intersection point here. Now I truly hope that the x values of those intersection points at x equals 0. Now if you're not confident with that, you can go ahead and plug in 0 for x and solve these equations. Again, you can set this equation equal to this equation, giving me 4 minus y squared equals to y squared minus 4, and solving for the y value. In doing so, I can go ahead and subtract the 4 from both sides, giving me negative 8. I can add the y squared to both sides, giving me 2y squared equals to 0, in which case I'll add the 8, divide by 2, and get 4 equals to y squared, giving me y equals to plus or minus 2. But wait a second, I thought we said x equals 0. Well, again, remember, if I plug x equals 0 into here, my y value will be plus or minus 2. Notice this is the negative 2 value for y, and this location here is y equals positive 2. Now, the detail that's most important to walk away from in this example is that if I were to attempt to slice this thing vertically, again, creating an integral in terms of dx, then what you'll notice is that the function that's on top is this one, and the function that's on the bottom is this one. You'll also notice that if I try to cut this in terms of dx, then I need f of x minus g of x, where all of the functions are in terms of x. Cutting this thing vertically actually causes a lot of hassle, because then I need this function here minus this function here, where those two functions are the same and they correlate to this function here. Okay, now if again you're having difficulty with this one here was I'm going to call that y2, I'm going to call this one y1. Okay, even though they're x's, I'm going to call them that way. So this function here is my y1, this function here is my y2. So you'll notice that y2 is upon itself if I'm cutting this vertically, and y1 is upon itself if I'm cutting this thing vertically. But there's another way I can do these problems. The other way I can do these problems is if I were to change the functions so that they're in terms of y's, and I cut the integral in terms of y's. Meaning, I'm going to go ahead and slice this thing sideways. And you'll notice by slicing it sideways, the y1 function is always on top of the y2 function. Something else you'll notice is that I'm trying to find a function in regards to y now, no longer in terms of x. When I say in terms of y, what I mean is that I'm going to have x equals some function of the variable y for both of these equations. And noticing that both of them are already in that form gives me a really solid opportunity. Now you'll also notice that I need y equals some number to another number, where again f and g are both the top and the bottom function. In this case, my y, a, is going to be that -2, and my b is going to be the +2. So I end up with the integral of y equals -2 to 2, where my top function is y1, so that's this function over here, and I'm going to replace my f of y with what it really is in terms of the variables of y, minus my g function, again, my bottom function here is y2. Now the question is why is that the top and that the bottom? Again, you need to reorient yourself thinking that the positive y-axis is the top location, and I'm cutting it down towards the bottom location of the negative y-axis. Okay, so again, you're cutting from the top, meaning the positive, in this case, sorry, positive x-axis to the negative x-axis. Again, it's very similar to what we did in previous examples where we're cutting down where the positive y to the negative y. We're cutting it from the positive x to the negative x. We're cutting it this way, again, from here over to here. So this y1 is definitely on top, and then my y2 is definitely on the bottom, giving me y squared minus 4 dy. Now, since everything is in terms of y in here, all I'm going to do is I'm simply going to integrate this function in terms of y. I'm no longer going to consider x as my integration variable because it says differentiate in terms of y, or integrate in terms of y. So I'm going to do this carefully. I'm going to first distribute this negative and combine like terms, giving me negative y squared minus y squared is integral of -2y squared, and negative times negative is positive, so positive 8. And I'm going to have y equals -2 to 2 dy. So when I go to integrate this, I'm simply going to, again, increase the power of y and divide by that new power, giving me -2y cubed divided by 3 plus 8, and now it's not going to be 8x because I'm integrating in terms of y, so I'm just simply adding the variable of y. This is integrated from y equals -2 to 2. I will then plug in 2 as my upper bound, and then I will plug in -2, giving me, I'm going to move it over here, -2 times 2 cubed divided by 3 plus 8 times 2, I'm going to throw that thing in brackets, minus, plugging in the -2 case, giving me -2 cubed divided by 3 plus 8 times a -2. Very carefully, I'm going to try and simplify this as much as possible. You'll notice here that this is going to end up being a -2 to the 4th, which is 2, 4, 8, 16 over 3. I'm going to have here plus 16. And then I'm going to distribute this negative into here. Now, you'll notice right here that this will end up being a positive same value here. But because of that subtraction sign, it's going to change it to a negative. So I'm going to have another -16 over 3. Don't forget that you have to distribute the negative into here as well, giving me negative, so it's positive 16. In which case, I'm going to end up having 32 minus 32 over 3. Okay, and if we want to, we can find a common denominator, multiplying this thing by 3 over 3, giving me a 96 over 3 minus 32 over 3, giving me a total of 64 over 3. Again, you'll notice once again that regardless of this area being cut sideways, I still end up with a positive area. And again, if this comes out negative, it means that we definitely did something wrong picking one function as the top where the other function should have been the top. That completes the integration of the area between two curves using the variable of y instead of x.